Good morning, everyone. I'm Monish. I work at Flipkart in the search team as an architect. Um, what's interesting is that over the next 35-40 minutes, I'm going to talk about how we really optimize the scale here. A little bit about me. I have a close to decade of experience working scaling interesting complex distributed systems. Since last 3 years, I've been working in search team, and we with my team we have been working on pretty interesting and challenging problems, solving them in a very novel way. And this talk is more about some of these work that we have done. Before I start, it's very important to understand why is search important at Flipkart. Search or organic search actually accounts for over 40% of the units that are sold at Flipkart, and this is huge money. The rest of the units sold are accounted by some inorganic search channels like recommendations or merchandisings. And interesting to note that these inorganic channels as well talk to search as a backend to get the content created in an ordered way. Hence, what we are talking of is a very important responsibility of making sure that we don't just serve the content in a very relevant way, but also in a very compute optimized way. And that's the subject of this talk. What I'm going to take you through in the next 35, close to 40 minutes is our architecture at search. This is a very high level diagram. I'm going to talk about what exactly scale that we really see at, and some interesting challenging problems that happens on the down in the inverted indexes. We're going to talk about matching, ranking and all that. And then I'll move on to some interesting novel ways that we have fixed some compute challenges and hence optimize the system. Moving on, when the pointer helps me, yes, it is. So this is a high level platform or a search component or a logical view that we have. This is not a deployment diagram, by the way. What we have on the top we call is search federator. In the middle, what we have is search broker. And the last one is the actual core, which is the index. Let's start with one-on-one, starting with search federator. Federator is a system on the top of the funnel, on top of the architecture at search. The prime responsibility that it has is to blend different type of contents to be shown to the user. What we have learned over time is the search browse page that you see on the app or a Flipkart website is not just set of products being shown in a list or a grid type of view. What we have there is a pretty rich type of an experience. What you see there is some ads, not just products. We see there is some rich content which is having some filters down there. There could be some visual elements there, and then so on. What Federator does is it blends all these content together and then show it to the user. What Search Federator as an architecture is also is a reverse proxy or a gate to the whole system, which means this is where all our clients talk to. While it is a reverse proxy, it does typical use cases like it would do caching for you, it would do ABs, and it would do some other complex rule matching as well. Moving on to the next layer, which is the middle one, we call it search broker. Search broker has two prime responsibilities. The first one, this is a place where we convert or try to get the intent behind the query that you are trying to request to. What I mean by that is, take for example, if you're searching for something like say Adidas white shoes, this is a layer which is going to convert such unstructured query to a very structured one. What I mean by that is, it is going to convert such query and then tag it and understand that Adidas that you meant here was brand, and then say white, what you meant there was color, and then so on. We use CRF, which is a machine learned model, very contextual, which helps us define such tags to a query or make it very structured, and also assigns a relevance weight to them. We call it relevance score, and it's needed for the relevance matching down there. What this layer also does is spell check and augmentation. What I mean by that is, say if you're searching for something like Puma bags, and say for some reason Flipkart doesn't have Puma bags, what we're going to show is just bags. We're going to drop the term called Puma. Or for that case, we can actually replace it with Adidas bags if really we have selection for them. This does spell check also. It also does deductions, which is an interesting thing. So if you're searching for mobiles under 10,000, this is a layer which is going to understand your intent that you're looking for category called mobiles, and what you're looking for a price range under 10,000. While intelligence layer or semantic is important, there's another important responsibility that this search broker does. What it does is, it finds the category specific ranking function that is to be applied, and then makes a distributed search to the layer below, the layer which is called index. And then it gets the top K and then does an n-way merge sort and then gives it back. The layer below was an index layer, which is giving back the actual products to the user. And hence, this search broker layer, when it gets those products, has a capability of re-ranking those products based on some fresh signals, like making sure the results are actually in stock, which is just going to be returned back to the user. Moving on to the last layer, we call it search index. This is the heart of the system. This is a layer which does a heavy lifting of matching across millions of documents, scoring them, and then giving back to the user. So like a typical search problem, we match millions of products. What users are looking for is just top 100 or top 10 of them. Hence, we have a problem of finding which among the millions of matching sets is to be shown to the user. What we do there is, we apply a complex scoring function, score all of these matching millions of documents, get the top 10 or top 20, whatever you're asking for from it, and then give it back to the user. Interesting to know, this is a layer where the most expensive operation we are doing is scoring. Scoring is very compute expensive operation on the course. And hence what I mean here is that on these layers, what you're going to choke is CPU well before you're going to choke network, or for that case even memory for the class of boxes that we are running with. We run with close to 30,000 cores here, that is 1,000 to 2,000 VMs that we are running here with. While management is important, also important here is to understand that if I do any compute optimization at this particular layer, which is having the huge number of boxes, the hardware that I'm going to save is being a interesting cost saver for us. I'll go a little more deep into the layer, which is again the indexing layer, the last core layer that we have. This again is still a 10,000 feet view of how our index actually internally looks like. On the top, what you see is an ingestion pipeline. We almost listen to every generated signal in Flipkart needed for discovery. What you see there is we listen to availability. These are in-stock updates coming from Promise as a separate team. We listen to regional shipping charges, which means we know geo-based in our ranking. We listen to pricing and promotion updates. We have complete catalog, and then the whole seller master data updated with us in our indexes. All these data flow in from different systems through a stream ingestion complex pipeline, and then we push it to something called a NoSQL type of store, which is needed for Bootstrap. Like a typical Lambda architecture, what we also do is all these stream updates are pushed to a broker, the message queue. And this is where all the 1,000 to 2,000 VMs, the index layer I was talking of, are reading these fresh signals as they happen, and then they save it to something called in-memory NRT store. NRT is a tech innovation. There are enough Slash and talks to talk about it. I'll talk more about the actual arc that we have done. While fresh moving signals move through that pipeline, there are slow moving signals like catalog updates, say a keyword or a brand, which doesn't change that often. Those slow moving updates move through the other left pipeline and goes directly to Lucene indexes. At this time, it's interesting to know that we use Lucene and Solar as our tech for the search. While the user searches for some query, we match into the inverted index, which has been hooked into both NRT and then Lucene stores. And we do top of that a lot of faceting and then ranking. In the next minutes of the talk, what I'm going to do is I'm going to talk about only this particular layer, which is the index layer, which is the core or the heart of the system. I'm going to talk about what scale this particular layer gets, what challenges that we get in a typical inverted index for the scale of Flipkart. I'm going to talk about the custom solutions that we have written and how did we really optimize compute to save hardware and a lot of cost for Flipkart. Moving on, this is the scale that it looks like. The boxes or the histogram in blue that you see are the document size that we have in our indexes, which means each product that comes to us, we just save it in the index and then we call it a document in a typical Solar words. These documents are towards the left two bars that you see, are projection that we see it will be growing to. We actually expect the collection or a catalog size being growing to close to 1 billion very soon. The line in red is the QPS that we have supported all this while. We started with a meager 20,000 per second in 2015, and the last BBD at 2017 we were scaled to 145K per second. What is more interesting here to understand that as the hardware cost we have, just repeat, as the scale is increasing, both in the cases of the selection size as the document is increasing, or for that case even the QPS is increasing by the more users coming in, the hardware is very proportional to that. What I mean by that is, with the growing selection or QPS expected, we need really more hardware, and then we really have to compute, optimize these. Moving on, we use close to 30,000 cores and an aggregate of 120 TB of a RAM size in our cluster here. This is how we classify a query that comes to Flipkart. We have category queries, brand, facet, line, and product. And like you see, the queries that you make have an intent. On the left side, it's very broad intent. Towards the right, we see a very, very narrow intent. Take an example on the mobile, towards the extreme right, you see 16.41 for a product. What it means is, most of the users in mobile category are making a product queries, which means they are looking for a product query like Samsung S8. This is going to match just 10 to 20 products, and we are good here. The problem starts in the category queries, which is what's circled in vertical red there. In lifestyle, what's happening is people are searching for very, very broad intent queries like shoes or t-shirts. These are those queries which is matching millions of products. And like I said before, you're matching millions of products. We just have to give top 100 or 200 to the users back, right? And hence we have to score all of those millions, and hence the compute cost of getting the top K sorted and giving back. While in the last slide I was talking about scale challenges with hardware growing up based on the scale of docks and the QPS we are getting. This is more talking about the queries that we are getting itself is broad, and hence the problem. This is how the inverted index typically looks like. I'm going to talk about matching in the next slide, ranking. This is an inverted index. If you've not seen this before, it's very much like a book that you see. In the last, you see a glossary. In the glossary, what you see is multiple words written there, and then for each word, you see page numbers written there. Very similar to that, what we have is a term dictionary, where if you have the terms, for each of the terms, what you see on the right is a posting list, or the list of all the documents in the index which is matching. This is what is simplified and then called posting list, the list of document matching. We have multiple documents, multiple term queries in the term dictionary. Like you see here, brand Adidas is having a huge posting list, and then color white is having its own, and so on. Let's talk about the problems that we are having here. The way Lucene works is, it traverses the index from left to right in these posting lists. And hence, what happens, any new update which comes in, it gets added to the last of the linked list, like this. So this 12 is a new product that just got added to the catalog or our indexes. It gets added to the end. If it was really a popular or a fresh product, I would have loved to see this 12th product coming in the front. The reason being, Lucene passes it from the front, and it would have been good if I could have done some query optimization on that. So while this was an order type of a problem that we see in inverted index at our scale, we also have problems like size being there. See the last one in the term dictionary, it says store called shoes. This is a set which is matching millions of documents down there, right? And since it's matching millions of documents, this whole posting list is running into huge set. Lucene does a decent way of making sure this is memory optimized by encoding them into the blocks, like you see here. However, the problem is still there. This listing is huge, and then one node can possibly not fit it. Other problem we see is of disk seeks. The term dictionary that you see over there in the red is a huge set with a growing collection size. We don't just have 3 terms like brand Adidas, color white. We have millions of them sitting in there, and hence, for a typical query execution, what we need is to locate this as fast as possible. With that, let's look how a query execution looks on top of it. Taking the same example, say Adidas white shoes, which our intelligence layer would have already made to brand, Adidas, color, and all that. What we need to do here is to find this in the term dictionary as fast as possible, because this itself is a growing of millions of set. Hence, what Lucene gives us is something called term index. What it does is, it's a prefix-based try created, which means you just give it a term like brand Adidas, it's going to give an output, an offset. With that offset, you can quickly go to the term dictionary and then seek it. Now the problem statement here, we are doing 2 disk seeks. One, just to find brand called Adidas here, you're going one seek, going to the dictionary, you're doing the second seek and going to find in the posting list. And once you have the posting list, what you have to do is find all these 3 lists, you have to just go and intersect it and find the matching set. Intersection is itself a interesting problem where it's an O of A plus B plus C as a compute time. What Lucene helps us is with a lot of skip pointers and leapfrogging to advance, and makes sure that this is more a logarithmic cost. While this is matching, this is ranking. When we match millions of products, like I mentioned before, reiterating, you have to find the top K out of them, and hence you have to score them. While K is a small set that what users are asking for, the N is huge, which is the matching set. A typical N log K problem, our compute cost here for the broad queries is pretty linear to the size of the index that we are having. While you could shard such indexes to a very small one, but the problem we still have is the cost that you have to take for the compute is still linear to the distributed search you are making. And hence, the topic of the talk where we want to optimize the hardware here so that the cost of hardware is not growing with either the selection size, the QPS, or in this case, even the matching set, even if it increases. We want to cut that linear growth in hardware to more sublinear. Moving on. So these are the all challenges I just talked about. I'm just accumulating out in here again. I talked about there's a huge posting list, term dictionary. I talked about disk seeks being a problem at the scale of product, being searched at Flipkart. We have a problem of top K optimization, which means there's an K set of matching set. I want to find the top K. Its scoring is complex here. I did talk about multiple times that hardware is growing linearly to the growing selection size or the QPA that is expected of us. We want to make it non-linear. Why these were problems? These are the solutions we came up with. These are pretty novel ones. I'm going to go one-on-one with each of them. The first one is custom sharding and distributed search. This is an easy one to understand. So what we did was, we wrote our own custom sharding at Search and Flipkart. What we did was, we took the complete selection size, the whole catalog, we striped it into 3 parts. We call it business unit wise: books, electronics, and lifestyle. It helps us in isolation. Each of these clusters or collections are having multiple shards. Depending on the selection they have, we just go and add shards there. And each of these shards are having multiple replicas in itself. We use consistent hashing or a ring-based partition to make sure we shard the documents and then choose which document should go to which shard. While this helps us scale literally infinitely, which means as the selection size is growing, we just keep adding more shards. And as the query volume expected from us, usually on a BBD type of a scale event, we just add more replicas out there. And then we just scale out literally infinitely and horizontally. However, the problem of hardware needed for this, it's still linear and then still costly affair. Important to understand here is search is not a lookup problem. It is a distributed search or a scatter gather type of problem. What I mean by that is, when the user comes to our website, they are not looking for a particular document. They are looking for a query term like iPhone cases. And in more likelihood, such query like iPhone cases is going to match a lot of millions of documents, and then that is going to sprinkled across multiple shards. When the request comes, I can't go to only one shard. I possibly have to make a distributed request to all these shards in these cases, right? So now that causes an interesting problem in itself, which is called scatter gather problem. I'll talk about learnings that we had with such custom sharding and then distributed search. To start with, custom sharding. Like I mentioned before, we use Solar as a tech for search. Solar also comes up with something called Solar Cloud, which is their own version of distributed search problem statement. We don't use Solar Cloud for the reasons that we saw at our scale. This is very query time inefficient. What I mean by that is, the way Solar Cloud works is, every update that comes to the master is being sync returned to most of the slaves or most of the replicas. What I meant by that is, this is very query time efficient because all these slaves which are giving or getting this stream updates of signals, what they do is a duplicate work. So imagine you have a shard which is having hundreds of slaves, all of them doing a duplicate work of creating that inverted index or posting this. All of these replicas doing a duplicate work of, say, having a transaction log in memory and then flushing the index down to the disk. They're doing a duplicate work of even merging the segments, which is very expensive affair. And these are the shards which are, the replicas which are serving the users. I'm better off not wasting my CPU cycles on any of these, common update type of frameworks. I'm better off using these CPUs, which are very, very scarce resource, only for the user-served queries. And hence what we did was an old school way of going master-slave architecture, where all this common non-query type of workload is done only once on the masters. And all the other, where it's just about matching and then ranking, the query specific for the users is done only on the slaves. Just by doing this, we actually saved a lot of hardware cost by not doing CPU cycles being wasted on the common things which is not user specific. While we were doing our own custom sharding, what we did was also made sure the shards are done sharded really thin enough so that the whole index that we are talking of is always in memory. Remember in this last few slides I was talking about term dictionary, term index, and disk seeks needed there. What we could do in these cases is, since it's sharded very thin, we should have enough memory on those boxes so that the whole index is always in memory. And hence you're not doing any disk seeks, always reading from the page caches. And hence the system is really fast. Long poll. Long poll is an interesting learning for all of us here. We had it really, first time experience of these. Like I took an example of distributed search, right? Query like iPhone cases come in and then I have to make a distributed parallel request to lot of shards or replicas. In our cases, this parallel request, it goes to close to 40 machines, 40 shards. Well, it's quite possible one of the shards that you go to is running slow. It could be doing a GC, it could be doing some replication. We really can't, know what is it doing. What could happen is that one user request will be waiting on this one bad guy who has not responded yet, and then long poll the whole system. The rest 39 would have come back, the one guy is bad holding your request. This is a typical long poll problem. How we solved this was by interesting strategies which are heuristics. So what we did there was, when the user request comes, distribute it to a lot of 40 boxes. We know each shard will come back in what time. There's a heuristic for it. And if it has not come back by that time, we have to do is we make a second request to a different replica of the same shard. And hence now you don't have a long pole. A bad guy can't really make a request being waiting for long. Moving on, while I just talked about was our own distributed search request or custom sharding, this talks about cascade ranking. Like I mentioned a couple of times before, I'll iterate it again. The problem that we have at hand is the matching set is in millions. We have to find the top k out of it. To find the top k, you have to again have a scoring function on all of these millions of matching set. And that scoring function is what we call ranking function, which is very expensive for the boxes that we are talking here. The ranking function that we typically use is very specific to a category as well. Say if you're talking about a mobile as a category, the ranking function is very sensitive to mobile, to price. Say if you're talking about a furniture type of category, the ranking function is specific to the geo signals. The ranking function for say lifestyle is very quality sensitive. And hence ranking function is very complex beast. What we have there is a normalized log linear of multiple signals we listen to multiplied by the lot of weights, which is category specific. What cascade ranking says is you can cut down such ranking function into multiple ranking functions. What you could do is, like in this diagram, it could be a very less expensive ranking function running on a millions of matching set, which means since it's a less expensive ranking function, you might be scoring a lot less on these boxes. The compute operations are very less. This could be done at layer 0. This could get the top 100k documents out, and then layer 1 ranking function could be a little more expensive since it's running on a smaller set of 100k. And then on this 100k ranking function, you can get top 1000 of it and then give it to the next layer. This is called layer 0 and 1, a typical cascade architecture. While we are better off using layer 0 and layer 1 ranking functions on the same shard, one node or one box, because you're talking about 100k documents in here, and if you do it outside this one box, what is going to happen is that 100k documents is going to create a lot of network payload and scatter together cost on the top. While the top level 2 layer could be run in a different box. We call it search broker, where we do a level 2 ranking on these top 1000 sets. So just to reiterate, just by doing all this, we have cut down our CPU cycles by a lot. What we have done is actually we are scoring a lot less on these boxes. And hence we have saved the hardware cost as well here. While there's a challenge here, the last or the lowest ranking function that we really need is supposed to be really diverse. Take for example, the last ranking function we had, it's getting out 100k products out of it. And say on top of 100k, I really want to run some personalized algorithm. Let's say gender specific algorithm. What would I really need is, in this 100k, I should have equal number of products for both male and female. And hence diversity in the last layer is really important for the ranking function. While at layer 0 and layer 2 is something that we have already in production, layer 1 is something that is really interesting and still work in progress, I would mention. So I talked about two things, distributed search and custom sharding. I talked about cascade ranking. There's a third thing and very important that we did. Sorted tiered index. It's a very novel way of doing this. Very few in the industry do this, and it's pretty close to my heart as well. Custom sharding helped us to infinitely scale, like I mentioned, right? Growing selection size, we are just adding more shards. Growing QPS, we're just adding more replicas. That helps us scale literally infinitely, though the cost of hardware is really high. What we did here was a monolithic index being cut down into two parts. Sorry, this is running slow. Yeah. So what we did this was, we took our whole huge monolithic index, cut down into two parts. We call it base index and the delta index. What base index is, it's a nightly generated index to our offline MR jobs. It's very optimized and then sorted Leucine index created in the offline world. Because it's running offline, we can always take any expensive operation like sorting to be done on the whole index. Every night we generate such base index, and over the day, whatever update comes in, we just push it to something called delta index. And whenever the user request comes, we just make a parallel request to both base and the delta. If there is the same document that is coming out from base and delta, what we do is we just override the delta document on the base, because delta is really refreshed or the fresh ones. There are interesting challenges here as well. Say for example that you had the whole new documents created one night, and then one of the document was having a keyword called Samsung, and say for some reason it got updated and then went to the delta index and it has changed the keyword now to Sony. When the user request comes in, say for a term like Samsung, what's going to happen is delta will give you 0 results or no matching set. Our base will give you a very old stale data of Samsung, and then we may end up giving back to the user. The way we solved this was, any update coming into Delta, we just made sure we just gonna delete it from base as well. So take out from this slide is that we just sharded this index into two parts. One is a bigger one, which is base, which is generated every night, and another is Delta. And it is sorted by popularity. When I say optimize, it's a more Lucene parlance. What it means is that it's one segment created, a very query optimized, there's no deleted documents and so on. Let's understand how do we really create these base indexes, since it's pretty novel. What we have there is a workflow of multiple stages, which is very, very fault tolerant, which means any of these stages fails in between over the night, if we just go back and roll back and then replay the document so that there is literally no data loss. Imagine we are switching index in production over the night when all our on-calls are sleeping, you do something insane here. And hence this is taking care of all the optimized things. So I'll quickly run through the stages that we have. The first one, what we call is build index. Build index is a typical MR job. What it does is, we have all the catalog data sitting in something we call our edge-based store. Mapper just scans over all the regions in the edge-based core, and it creates something called solo documents, which is going and sitting in the index. These solo documents are very specific to our schema. There's a partitioner sitting in between mapper and the reducer. What it does is, partitioner takes the documents created from mapper, give it to the reducer in a custom sharding way that we implemented. Reducer is pretty novel. What we have there is an in-memory Solr server running in with an NIO-based directory. Why it's embedded Solr server? Because the index that we have at Flipkart is pretty complex because of scale we have. What we have there is products, and we have listings, and then listings is a child of products. A pretty complex hierarchical index, and hence the need for such reducer. By the end of this particular stage, what happens? We have multiple segments or multiple indexes created for single shard. The next stage is called sort index. It's a no-op mapper. However, the reducer works on the last stage where we had multiple segments created for every shard. This job or this stage merges all these segments and creates single segment for single shard. And it creates a nice optimized Lucene segment over there. We use a sorted custom merge policy there, again a custom to us, novel thing. While we are merging all these segments and then make a single segment for a shard, we also make sure we sort it. We sort it on something called popularity or RPI. This is more a machine learned model which gives us one value for every product that we have there, and hence we can always sort on that. By the end of this particular stage, what we have is one index created which is sorted, optimized, and then single segment created for every one shard, and then parallelly for all the other shards. With this, we just go a version stamp it, and then push it to a store for the DR reasons. Moving on to the next stage, we call it switch index. While the stage 1 and 2 was creating the index, stage 3 is switching the index in the night in our production masters. And hence, the masters now go talk to the ingestion stream topology and says, guys, stop giving me any more updates. It talks to all the replicas that it is, taking care of, the master. It says them, don't replicate for me because, I'm going to switch the index right now. What it also does is it purges the delta index, the updates that came over the day, because they are no more needed. The base index that we just created is already having them. And then we then go and then switch it on the masters. We bump it and run extensive health check suits on top of it. Like I mentioned, we have to be really making sure that the index that we are creating is healthy and then sane, and hence these health check suits are very, very comprehensive. Take for example, very recently we had a catalog outage where we ended up getting a lot of invalid or incomplete documents. What we did was this health check suit actually caught that and actually made sure that we roll back to an old state automatically over the night, and then we made sure also automatically that there is a replay doing and there is no data loss. That's what the last stage is for, replay and rollback if whenever needed. Moving on, like I mentioned, sorted tiered index is pretty novel. I just mentioned how we do it. This is how it helps as well. So it's interesting to understand in an e-commerce world, the way it works is the updates that we get is only 1% over a day. So we have a huge set of index, and it's only hardly 1 to 2% of the documents that are getting updated. If you don't do something like a sorted tier index generated every night, what is going to happen is over a month's time, whole index is going to be very memory fragmented, because you're getting updates almost every day. Posting list is going to be very, very memory fragmented in a very soon month's time. Typical memory fragmentation looks like this. However, what we did was, obviously we created a base index every night, which is a very static index. There's no change happening there. The changes are only happening in the delta, which is very small, 1% of the size of an index. And hence, what we got in return was a very less memory fragmented index. What this helps is because the memory is very less fragmented, there's very less CPU cycles happening there because of GC. We run a huge heap, and hence GC cost saved there itself is huge. Moving on, while fragmentation was less, the second thing that we got in return was early termination. Like I mentioned, the whole index nightly created is always sorted on popularity. Hence, what we could have always done, take the example that I started in the first slide, that the lifestyle queries we are getting is like very, very huge and inexpensive, matching millions of documents. In this typical example, this is a posting list for such lifestyle query, which is running into millions of matching set. And like I said before, reiterating, our problem statement was to find the top 10 or top 20 out of this matching millions of documents. What we are doing now is not scoring on all the millions matching set. We just take the top 100K always and then score only on these top 100K. Eventually what I'm saying is, irrespective of how big is the index size or how huge the selection is growing to, I can always take the top 100K and then always score on top of them. And hence, the problem of sublinear comes in. With the increasing size of the selection, this posting list growing, I'm always scoring only 100K, and hence my compute cost is always constant. While this works very well for a browse type of use cases, if you're searching for something, it's not so easy. Say if you're searching for something which is not so popular, what's going to happen? It's going to be in the extreme end of the index. I've just taken top 100K out of it. It's not popular. I'm going to just cut you off, which is not a good experience. Hence, to make sure we don't cut down on the relevancy on search, we run extensive heuristics. We understand that your query that you're firing is a category query, which is very, very broad, like shoes, or you're firing a query which is like a product query, like Samsung asset, which is anyways matching only 20 products. So we do this early termination only for the category set of queries, which is anyways matching millions of products. And for a category query like shoes, if I cut and then show you only popular products, you're good off. There's a problem of diversity and recall loss, and then this is still a little work in progress. However, we have got a huge increment with just doing early termination. Take an example of another world where distributed search happens. When you search for in Google for say Donald Trump, it shows 27 million products and above. It says it has claimed to finish this in 500 milliseconds. Obviously, it has not taken all those 27 million documents and then done some expensive ranking function and then showed up there in the top. What it has done is it has obviously early terminated it. The very fact that you see a count which is very rounded, it means they have actually early terminated. This is a very norm in the industry now. Going forward, I mentioned 3 compute optimization strategies: distributed search, cascade ranking, and then early termination with sorted base index. Let's summarize and stitch all this together. Like I mentioned, we have an ingestion pipeline which gets all possible signals. We store it to something called discover store, fondly known as discover storage base. We run an MR pipeline every night on top of this. And this is what it looks like. We run the MR pipeline on top of this and then build the index every night. And then every night we just go and then push this recently generated base index to our masters over the night. Now that it is always sorted by popularity, we could always early terminate it. When the user request comes, we just go hit our semantics layer, convert that unstructured query to a structured one, and then fire it in a distributed search way down to the shards or the index nodes. This is where the index search node comes. It federates the request both to the base index and the delta index, gets the documents back. And if you're running a very expensive type of a query, which is like matching millions of documents, like a category query, we're going to early terminate it. Over the day, whatever update comes, it flows in directly to the delta index. And yes, we use cascade ranking on top of it to make sure we are scoring very, very efficiently. Let's talk about the challenges I had mentioned in the starting. We talked about our term dictionary is huge. I talked about we are doing a lot of disk seeks, which is not good at the query time. I also talked about top K optimization. The problem statement, we are matching huge number of products and we have to score them and then find the top K. And then I also talked about the hardware that we are growing to with the increased selection size, over that case the increased QPS that we have to support is growing linearly. Let's see how we actually solve them by these. Just by doing a custom sharding, we made sure the posting list is always in memory. We made sure the term dictionary and the term index I was talking is always in the page caches, just by doing a custom sharding it thin. I mentioned we have an expensive ranking function. Just by doing a cascade ranking, what we are doing there is scoring a lot less, and hence the compute is getting saved. And hence expensive ranking function is not cut down into multiple ranking functions. I was talking about sublinear growth being expected. Hardware is growing expensive, and it's very proportional to the increased selection size or increase QPS, we ran a sorted tiered index with all determination to help us there. Moving on to a more summarization slides, just by doing a sorted tiered index, we got our latencies down by 70%. Just because it was less memory fragmented, the boxes actually started showing up a high throughput. Our latencies were down, and hence the CTR or the business metrics that we saw also started seeing an uptick. We got our CTR and checkout per visit up by 8 and 3 bps respectively. These are the Flipkart scale. Moving on to the last slide, our fourth event, BBD. This is how we looked like in 2015. We had close to 40 million type of a selection size or the number of documents. And we were serving at that time close to 20,000 queries per second. This is a time when we had no sharding, which means single box was hosting all these 40 million documents. We had a tough time at that time. We were not able to vertically scale up. We were going out of memory. We wrote our offline cache refreshers so that user don't see the latencies that we are really gonna show up them to. BBD 16 was pretty interesting. We had close to 2800 VMs. This is 60,000 cores. Our selection size literally went up by 3 times by that time, 40 to 120 million. The queries that we were supporting by that time was 80,000 per second. That's healthy. By this time, we had a custom sharding implemented, we had NRT, we had geo-based ranking signals and all those complex things. BBD 17 was pretty interesting. We literally cut down our hardware footprint by half to 1380. Though our selection size literally went up by 3 times to 338 million. And we supported a very healthy 145K queries per second. We actually managed to give back 24,000 cores as a part of Kube release to the IS as well. But we are still waiting for the team to treat us for that. But yes, that summarizes our talk. Thank you so much. Please shoot your questions if you have, and I still have time for them. Thank you.
Question while I was looking on the on-call issues, but this is regarding the customized sharding that you're doing, and so you have a base and a delta, and now I'm assuming that you won't be applying the delta on the base. Actually, you'll be keeping them separate, but when the query comes, you'll be giving some weight so that you can answer the queries from the data from the base as well as delta. So how that weight is calculated, or you do a recomputation of merging something?
So the way this works is that we just made our index cut down into 2 parts. There are 2 cores sitting in the index. So like you understand the solar, we can always shard your indexes into 2 multiple cores. What we have there is we just cut down our index into 2 parts. We just call it base index, which is nightly generated, and then we have something called delta index, which is having all the updates that came over the day. What it means is that any update that came to a document is just sitting in the delta index, which is something like down there. But although the new updates, the old updates are sitting over there. Right? When the query comes, we actually make a parallel request to both of these and then merge the documents. We get the data from both delta index and then some.
You have to compute the result that comes again, and you have to compute, some sorting or some computation.
That's right.
So that's not heavy?
Yeah, I'll talk about it. So we do a compute on the base index, which is the top K ranking function. The base index is gonna get me the top K set, which is like millions of matching, postal lists and all that. It'll give me top K best results. And so is delta index is gonna give me the top K set. What I'm going to take is both of these top K, merge it. If there's a same document that came from both, I'm just taking priority for the delta index, and then I'll get back both top Ks together and give it to the layer which is above. It's called broker layer, which does an again n-way merge sort on all the responses and then finds the best score out of all of this. So hence the scoring function is running both on the base index and the delta index. The scoring function is still same which is running over there. Just that scoring function is a lot more efficient on the base index because it is it's very query performant and things like that. Interesting question. So the question was that how are you handling, I'm repeating the question, yes. So the question was that how are you handling network partition in such custom sharding that you guys implemented? So like I mentioned, we went back with a very easy way of making sure master slave as an architecture. If you're talking about the solo cloud world, where is all these problems of network partition actually come in? Because there's no one single master there, right? What happens, update could be coming in from different places and going into the different masters. And master itself could be getting switched because of network partition. By doing a simple single master, we made sure updates either go to this master or don't go to this master. It's a single node, either it goes through or it doesn't go through. We take care of all the other problems that, if the master is down or, it's not HA in our stream ingestion pipeline. What we do is, if the update doesn't go to the master, the stream ingestion pipeline slightly backlogs, and when this guy comes up after the network partition has been cleared up, we just take the updates there. While we are also working on interesting solutions around making this master itself HA by making 2 calls to 2 different masters. And hence we really don't have the problem of actually network partition. By the way, Solo Cloud would definitely have a problem of network partition, and the way they handle, I guess, is by making sure they are more available and not consistent, or sorry, more consistent and not highly available.
And you have only one master in HA for
That's right.
all the...
No, we have close to 40 or 30 shards. Each of these shards have multiple replicas and only one master. While this makes a little bit, always be sure that you are having only one master, and hence no partitioning and all those problems. And hence, you go by a simple solution, it's always going to help you, is what I see. You can handle the other HA problems on the master by different views. Yes. Not really. So if you see Solar 7, the way it works is, it really cut down on the Solar Cloud, because most of the people like our scale were not even adopting Solar Cloud for their distributed search. They came up with Solar 7, where they said that we'll go back to something like a master slave of type of thing, where you can just have a transaction log being pulling in. While we are still trying with Solar 7 right now with our indexes to see how performant it is, but the updates are still going to all the masters, all the slaves, right? So there's a transaction log still there, right? Right? So what we're talking of, there's something which is occupying my memory, which is called transaction log. I really don't need all these, right? I have slaves which possibly can be very, very compute intensive, and then save all my CPU cores only for user load, and then save a lot of cost. We could do one thing, basically we can possibly talk offline on 30 minutes where I'll be available for more complex chat on that. Yeah. I guess that we are mostly done. I'll be available, maybe Umesh, we can again chat on for next 30 minutes on there. Thank you so much, guys. Thank you.